There's something humbling about gazing up at the night sky, isn't there? The stars shimmer like distant lanterns, and for a moment, you might feel like you've got the universe figured out. But what if I told you that beyond those familiar constellations lies a realm of mysteries so profound they shatter our understanding of reality itself? We're not just talking about unanswered questions, we're diving into cosmic paradoxes, those mind-bending riddles that defy logic, twist the laws of physics, and leave even the most brilliant scientists scratching their heads. These aren't just gaps in our knowledge, they're glaring contradictions that force us to rethink everything we thought we knew about space, time, and existence. Take black holes, for example. These cosmic monsters don't just swallow light, they seemingly erase information from the universe entirely, violating one of the most fundamental principles of physics. Or consider quantum particles, which can communicate instantaneously across vast distances, as if the speed of light were just a suggestion. And what about the unsettling idea that our entire universe might be a holographic projection, a mere shadow of some higher dimensional reality? These aren't plot twists from a sci-fi novel. They're real paradoxes that keep physicists awake at night, wrestling with concepts that challenge the very foundations of science. So why should you care? Because these paradoxes aren't just academic curiosities, they're clues. Each one is a breadcrumb leading us closer to a deeper truth about the cosmos, hinting at realities far stranger than we've ever imagined. By exploring them, we're not just satisfying our curiosity, we're peering into the edges of human understanding, where the rules break down and the impossible becomes possible. Over the course of this journey, we'll unravel 20 of these cosmic conundrums, each more bewildering than the last. By the end, you might find yourself questioning not just the universe, but the very nature of reality. Ready to dive in, the cosmos has been waiting to blow your mind. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Statistically speaking, the sheer number of planets orbiting in habitable zones should mean the cosmos is teeming with life. And yet, when we listen, when we search, we hear nothing but silence. This eerie absence of extraterrestrial voices is the heart of the Fermi Paradox, a cosmic riddle that asks, if life is so likely, where is everybody? Think about it. Our galaxy alone is around 13.8 billion years old, and Earth is a relative newcomer at just 4.5 billion years old. If intelligent civilizations arose even a few million years before us, a mere blink in cosmic time, they would have had more than enough opportunity to spread across the stars, leaving traces of their existence everywhere. So why haven't we found them? Why no alien megastructures, no interstellar broadcasts, no visiting spacecraft? The silence is deafening, and the possible explanations only deepen the mystery. Some scientists suggest that advanced civilizations inevitably self-destruct, whether through war, environmental collapse, or unchecked artificial intelligence. Others propose that spacefaring species might be so rare that the distances between them are simply too vast to bridge. Then there's the unsettling possibility that we're being intentionally avoided, that Earth is quarantined, either because we're too primitive or because contact would be too dangerous. Or perhaps the truth is even stranger. What if we're among the first? What if intelligent life is such a fluke that the universe is only now waking up to its own potential? The Fermi Paradox forces us to confront uncomfortable questions about our place in the cosmos. Are we a cosmic accident, a lone spark of consciousness in an otherwise lifeless void? Or are we simply too early to the party, destined to be the ancient civilization that future species wonder about? Either way, the silence of the universe isn't just a scientific puzzle, it's a humbling reminder of how little we truly understand. And until we find answers, the stars will keep their secrets, leaving us to wonder if we're alone in the dark. If black holes are the universe's ultimate shredders, then the information paradox is the receipt we can't find proof that something vital has gone missing. Here's the problem. Quantum mechanics insists that information, the fundamental blueprint of reality, can never truly vanish. It might get scrambled, tangled, or hidden, but it's always preserved. Yet black holes, those cosmic vacuum cleaners, seem to laugh in the face of this rule. When matter crosses their event horizons, it's not just crushed into oblivion, it's as if the very details of what fell in are erased from existence. This isn't just a quirk, it's a direct collision between two pillars of physics. Einstein's general relativity says black holes consume everything, while quantum mechanics says, not so fast, information must survive. Stephen Hawking threw gasoline on this fire when he discovered black holes aren't entirely black. They leak energy, slowly evaporating over eons through what we now call Hawking radiation. But here's the catch. That radiation appears random, carrying no trace of the information swallowed by the black hole. It's like burning a library and claiming the smoke particles contain every book's contents except no one can read the smoke. This realization sent shockwaves through physics because if information is truly lost, it undermines our ability to predict the past or future, turning science into a guessing game. Desperate for solutions, theorists have proposed wild ideas. Maybe information isn't lost but encoded on the black hole's surface, like a hologram, where two-dimensional boundaries hold secrets of three-dimensional space. Or perhaps black holes aren't endpoints but portals, with information tunneling into alternate universes. Some even suggest black holes never fully evaporate, leaving behind microscopic remnants that hoard the missing data like cosmic time capsules. But each theory comes with its own headaches, stretching our understanding of reality to the breaking point. The stakes couldn't be higher. If information can vanish, it means the universe has a built-in delete button, a flaw in the fabric of causality itself. But if it persists, hidden in ways we can't yet see, then reality is far stranger than we imagined. Either way, the black hole information paradox isn't just about star-devouring anomalies in deep space. It's a mirror held up to the limits of human knowledge, showing us how much we still have left to unravel. And until we solve it, we're left staring into the abyss, wondering if the universe keeps perfect records, or if some secrets are meant to stay swallowed. Time travel isn't just the stuff of science fiction, it's a theoretical possibility that comes with one of the most baffling paradoxes imaginable. Picture this: you build a time machine, journey back to the past, and accidentally prevent your grandparents from ever meeting. Without their union, your parents would never exist, which means you could never be born. But if you were never born, how could you have traveled back in time to disrupt their meeting in the first place? This is the grandfather paradox, a dizzying loop of cause and effect that threatens to unravel the very fabric of logic. At its core, the paradox exposes a glaring flaw in our understanding of backward causality, the idea that an event in the future can influence the past. If time travel were possible, every action you took in the past would ripple forward, potentially erasing the conditions that allowed your journey to happen. It's like a snake swallowing its own tail, a self-defeating cycle that defies resolution. Physicists and philosophers have wrestled with this problem for decades, proposing wild theories to untangle the knot. One popular solution comes from the multiverse theory, which suggests that every decision spawns a new, parallel timeline. In this scenario, your meddling in the past wouldn't erase your own existence. It would simply branch off into a separate reality where you never existed. while your original timeline remains untouched. It's a cosmic escape hatch, allowing for time travel without the messy paradoxes, but even this idea raises thorny questions. If infinite alternate universes exist, does that mean every possible version of events is playing out somewhere? And if so, does our version of reality hold any special significance? Another theory, known as the self-healing timeline, argues that the universe has a way of correcting inconsistencies. No matter how hard you try to alter the past, some cosmic safeguard would always intervene to ensure events unfold as they originally did. Maybe your grandfather would survive your assassination attempt through sheer luck, or some unexpected twist would bring him and your grandmother together anyway. This idea paints time as a rigid, unchangeable structure where free will is an illusion and destiny is written in stone. But perhaps the most unsettling possibility is that the grandfather paradox isn't a flaw, it's a feature. Maybe the universe simply doesn't allow time travel to begin with, enforcing a kind of cosmic censorship to prevent logical inconsistencies. If that's true, then the paradox isn't just a thought experiment. It's nature's way of slamming the door on time travel before we even try. Whatever the answer, the grandfather paradox forces us to confront profound questions about causality, free will, and the nature of existence itself. It's a reminder that time, even in theory, isn't just a dimension we can hop through like stepping stones. It's a labyrinth of cause and effect, where every turn could lead to a contradiction. And until we crack this puzzle, the idea of changing the past will remain one of the universe's most tantalizing and terrifying what-ifs. Imagine holding a map with most of its landmarks erased, streets, cities, entire continents, all missing. Now picture that map as our understanding of the universe, because here's the unsettling truth. Everything we see, stars, galaxies, planets, makes up less than 15% of what's actually out there. The rest is an invisible force we call dark matter, a ghostly presence that refuses to show itself yet holds the cosmos together with its gravitational grip. It's like trying to solve a jigsaw puzzle where most of the pieces are transparent. The evidence for dark matter is everywhere, just not in ways we can touch or see. Galaxies spin so fast that, by all rights, they should fling themselves apart. The only thing keeping them intact is the gravitational pull of something we can't detect. Light bends around empty patches of space as if invisible hands are warping the fabric of reality. Even the way galaxies cluster together hints at a hidden scaffold of mass, an unseen architecture shaping the universe. But after decades of searching, we've yet to catch a single glimpse of what's really there. Scientists have thrown every tool at this mystery: particle colliders, underground labs, space telescopes, hoping to catch dark matter in the act. Some theories suggest it's made of WIMP, weakly interacting massive particles that pass through ordinary matter like ghosts through walls. Others propose actions, hypothetical particles so light they barely register. But despite countless experiments, dark matter remains stubbornly out of reach. The longer it eludes us, the more radical the explanations become. Could we be wrong about gravity itself? Maybe Einstein's equations break down at cosmic scales, and what we call dark matter is just gravity behaving in ways we don't yet understand. The implications are staggering. If dark matter is real but invisible, it means we're surrounded by an entire shadow universe, unmapped and uncharted. If it's not real, if our grasp of gravity is flawed, then centuries of physics might need rewriting. Either way, this isn't just a gap in our knowledge, it's a canyon. And until we bridge it, we're left navigating the cosmos blindfolded, sensing a presence we can't prove, guided by a force we don't fully comprehend. The universe is whispering its secrets, but dark matter keeps them just out of earshot. What if simply watching something could freeze it in place? This isn't science fiction. It's the quantum Zeno effect, one of the most mind-bending quirks of the subatomic world. Named after an ancient Greek philosopher's paradox about motion, this phenomenon reveals something startling. The act of observation doesn't just measure reality, it can actively alter it. Here's how it works. Imagine an unstable particle, like a radioactive atom on the verge of decay. Left alone, it will eventually break down, but if you continuously observe it, something extraordinary happens. The particle resists change as if your gaze pins it in place. It's like staring at a pot of water, waiting for it to boil, except your watching somehow keeps the water frozen. This isn't just theoretical. Experiments with atoms and photons have shown that frequent measurements can dramatically slow down or even halt quantum processes. The more you check, the more the system behaves like a deer in headlights, trapped in its initial state. At its core, the quantum Zeno effect blurs the line between observer and observed, raising a haunting question. Does reality only solidify when we're looking? Some interpretations of quantum mechanics take this even further, suggesting that consciousness itself might be the glue that holds existence together. Without an observer, could the universe remain in a fuzzy, undefined state? But before we spiral into solipsism, there's a crucial distinction to make. Observation in quantum mechanics doesn't require a human mind. It simply means any interaction that forces a particle to choose a state. A photon hitting a detector counts as much as a scientist scribbling notes. Yet, the implications still rattle our intuition. If measurement can freeze time on a quantum scale, could there be deeper layers where observation shapes reality in ways we don't yet grasp? Philosophers and physicists have wrestled with this for decades, from Copenhagen's collapse of the wave function to the many worlds interpretations branching timelines. The quantum Zeno effect isn't just a laboratory curiosity, it hints at a universe far more interactive than we ever imagined. What if black holes or dark matter behave differently when unseen? Could ancient starlight, untouched for eons, hold secrets that vanish the moment we point a telescope? Every time we probe these questions, we're reminded that reality might not be a fixed stage but a dance between the seen and unseen, where the observer is never just a spectator. And that's a paradox that doesn't just challenge physics, it redefines what it means to exist. What if everything you know, your memories, your sense of self, even the world around you, was just a random glitch in the fabric of reality? That's the unsettling premise of the Boltzmann Brain paradox, a thought experiment that turns the nature of existence into a cosmic dice roll. Named after physicist Ludwig Boltzmann, this idea emerges from a chilling statistical possibility. In an infinite universe governed by entropy, the random motion of particles could, by sheer chance, assemble a fully formed, self-aware brain out of nowhere. Not attached to a body, not born from evolution, but a lone, floating consciousness complete with fabricated memories of a life it never lived. Let that sink in for a moment. If the universe has existed for eternity, or if it cycles through endless expansions and contractions, then the odds of such a brain spontaneously forming, though astronomically low, aren't zero. In fact, given enough time, it becomes more likely that a disembodied brain would pop into existence than an entire ordered universe like ours. So here's the nightmare question. How do you know you're not one of those accidental minds hallucinating reality in a void where nothing else exists? The coffee you drank this morning, the device you're holding right now, even the stars above, all could be elaborate illusions conjured by a brain that blinked into being a second ago, armed with false memories of a past that never was. Scientists and philosophers recoil from this idea, not just because it's unsettling, but because it exposes a gaping hole in our understanding of time and probability. If the universe tends toward disorder, why does it contain so much structure? Why aren't Boltzmann brains more common than coherent, stable beings like us? Some argue that our very existence disproves the paradox after all. If random brains were the norm, we wouldn't see the consistent, predictable laws of physics we observe. Others counter that we might be living in a rare, low-entropy bubble, a temporary pocket of order in a sea of chaos, making us the statistical outliers. Then there's the multiverse angle. If infinite parallel realities exist, then somewhere, a Boltzmann brain really is floating in the abyss, convinced it's reading these words. But does that mean we should doubt our own reality? Not necessarily. The paradox isn't a proof that we're illusions, it's a warning about how little we grasp the foundations of existence. It forces us to ask what, if anything, makes our consciousness more real than a hypothetical fluke of physics. Perhaps the most profound takeaway isn't about brains at all, but about the nature of certainty. Science relies on observation, but what if observation itself is untrustworthy? The Boltzmann brain paradox doesn't just challenge cosmology, it shakes the bedrock of epistemology, the study of how we know things. In the end, the only solace might be this: whether we're fleeting fluctuations or enduring beings, our experience feels real, and in a universe full of mysteries, that might be the only anchor we have. Picture two identical twins. One straps into a spaceship and blasts off at nearly the speed of light, while the other stays comfortably on Earth. When the traveler returns decades later, they step out looking barely older, while their Earth-bound sibling has aged decades. This isn't a sci-fi plot, it's the twin paradox, a real consequence of Einstein's theory of relativity that warps our most basic intuitions about time. But here's where it gets messy. From the astronaut's perspective, Earth was the one hurtling away at light speed, so shouldn't the people on Earth be the ones aging slower? How can both twins see each other as the younger one? The answer lies in a subtle but crucial detail: acceleration. Unlike the steady motion of Earth, the traveling twin experiences something their sibling doesn't: a dramatic change in speed. To turn around and come home, the spaceship must decelerate, reverse direction, and accelerate back toward Earth. That shift breaks the symmetry between the two frames of reference. While Earth's gravity gently tugs at the stationary twin, the astronaut's body is slammed by forces that literally rewrite the rules of time. General relativity tells us that acceleration and gravity are two sides of the same coin, bending spacetime like a trampoline under a bowling ball. So when the spaceship fires its engines, it's not just changing velocity, it's altering the very fabric of reality around the traveler. But the implications go deeper than just clocks ticking at different rates. This paradox reveals time as a fluid, personal experience rather than a universal constant. GPS satellites orbiting Earth already account for these relativistic effects. Their clocks run slightly faster than those on the ground, and without corrections, your phone's navigation would drift off course within minutes. Imagine a future where interstellar travel is routine. A crew visiting a star 20 light-years away might return to find Earth 40 years older, while they've only aged a decade. Families would reunite across generational divides, with parents outliving their own children. It's a haunting reminder that time isn't just something we measure, it's something we live, and relativity can stretch that lived experience in ways that feel almost cruel. The twin paradox doesn't just challenge our understanding of physics, it reshapes how we think about existence itself. If time is this malleable, what does that mean for concepts like destiny or free will? Are our lives just threads woven into a four-dimensional tapestry where past, present, and future coexist? Einstein himself grappled with these questions, famously consoling a grieving friend by suggesting death might be an illusion, that from the universe's perspective, every moment persists eternally. Whether that's comfort or cosmic horror depends on your perspective, but one thing's certain: the twin paradox proves reality operates by rules far stranger than our everyday instincts suggest. And in that strangeness lies both mystery and possibility, a universe where time bends but curiosity never breaks. Stand outside on a clear night, and the sky seems infinite, a vast expanse dotted with countless stars. But here's the puzzle. If the universe truly is endless and unchanging, shouldn't every inch of that darkness be blazing with starlight? That's the essence of Olbers Paradox, a deceptively simple question that unravels some of the cosmos' deepest secrets. In a static, infinite universe, every direction you looked would eventually land on a star, like standing in an endless forest where trees block the horizon in every direction. The entire night sky should glow as bright as the surface of the sun, yet instead we're greeted with darkness. So where's all the missing light? The answer lies in the fact that our universe isn't static, it's expanding. Edwin Hubble's groundbreaking observations in the 1920s revealed that galaxies are racing away from each other, stretching the very fabric of space. This expansion does something extraordinary to starlight. It shifts it toward longer, redder wavelengths, a phenomenon we call redshift. Over vast distances, this stretching saps the energy from light, dimming it until some stars fade from visibility entirely. Even more crucially, the universe hasn't existed forever. The Big Bang, roughly 13.8 billion years ago, means light from the most distant stars hasn't had time to reach us yet. We're not just looking out into space, we're peering back in time, and eventually we hit a wall, the cosmic microwave background, the afterglow of the universe's fiery birth. Beyond that, there's simply nothing more to see, but there's another twist. Interstellar dust floating between stars absorbs some starlight too. Yet even this can't fully explain the darkness. Dust would eventually heat up and re-emit the energy, lighting up the sky anyway. The real revelation here is that Olbers' paradox isn't just about light. It's a breadcrumb trail pointing to the universe's dynamic nature. If the cosmos were infinite and eternal, we wouldn't exist to ponder the question. The very fact that the night sky is dark tells us the universe had a beginning, that it's evolving, and that it's finite in age. This paradox also forces us to confront the limits of our perception. Our eyes can only see a narrow slice of the electromagnetic spectrum. What if the darkness is an illusion? Perhaps the sky isn't truly dark but filled with wavelengths invisible to us, from radio waves to gamma rays. Or maybe the universe's expansion will one day stretch starlight so thin that the night sky will fade to black permanently, leaving future civilizations with no stars to guide them. Olbers' paradox reminds us that sometimes the simplest observations, like a child asking why the sky is dark, can unlock profound truths. It's not just about missing light, it's a window into the universe's birth, its structure, and its ultimate fate. Every time we gaze up at the stars, we're witnessing a cosmic story written in shadows, one that began with a bang and may end in silence. And that's a mystery as humbling as it is illuminating. What if the world around you, the warmth of sunlight, the taste of coffee, even the weight of this sentence in your mind, was nothing more than lines of code in an unfathomably advanced simulation? This is the simulation paradox, a thought experiment that turns our understanding of reality inside out. The logic is unsettlingly simple. If civilizations eventually gain the power to create hyper-realistic virtual worlds inhabited by conscious beings, then statistically, the number of simulated minds would dwarf those in the original universe. So by sheer probability, you're more likely to be one of those simulated entities than a flesh and blood human in the base layer of reality. But here's where it gets thorny. If we're living in a simulation, why does everything feel so seamless? Where are the glitches, the floating point errors, the texture pop-ins, the cosmic shortcuts a programmer might take to conserve processing power? Some theorists argue we might have already found them. Quantum mechanics, with its particles that exist in multiple states until observed, behaves suspiciously like a render engine optimizing resources. The speed of light could be a hard-coded limit to prevent system overload. Even déjà vu might not be a trick of memory, but a residual artifact of a save file reloading. Yet for every potential glitch, there's a naturalistic explanation, leaving us trapped in a loop. The better the simulation, the harder it is to prove it exists. The paradox forces existential questions that ripple far beyond physics. If we're simulations, do our choices matter, or are we following predetermined scripts? Does the programmer watch us like characters in a game, or are we background processes in some alien school project? And what happens if we ever crack the code? Would our creators hit the delete key? Some scientists, like Neil deGrasse Tyson, put the odds at 50-50 that we're living in a simulation. Others, like physicist Sabine Hossenfelder, dismiss it as modern-day solipsism, a high-tech repackaging of Descartes' evil demon, untestable and therefore unscientific. Yet the simulation hypothesis isn't just philosophy, it's bleeding into science. Researchers have proposed experiments to look for pixelation in high-energy cosmic rays or anomalies in quantum behavior that might betray underlying computation. Billionaires secretly fund efforts to break out of the simulation, while some AI experts warn that if we ever create conscious simulations ourselves, the ethical implications would be staggering. After all, if you can't prove you're not a simulation, how do you justify pulling the plug on one you've made? Perhaps the most haunting twist is this: even if we are simulations, it changes nothing about our lived experience. Pain still stings, love still resonates, and the stars still beckon with their ancient light. The simulation paradox doesn't just ask whether reality is real, it asks whether that distinction even matters. In the end, the universe, simulated or not, is the only one we've got. And until we find a way to peek behind the curtain, we're left to live, wonder, and code our own meaning into the pixels of existence. Time loops aren't just for science fiction, they might be woven into the very fabric of reality. Take the Bootstrap Paradox, a cosmic riddle that asks, what if the universe is a closed loop with no true beginning or end? Picture a time traveler handing a young Einstein a notebook filled with his own groundbreaking theories. Einstein publishes them, becoming famous, but who actually wrote those ideas in the first place? The information seems to come from nowhere, a self-contained cycle where cause and effect chase their own tails. Now stretch that idea to the scale of existence itself. What if the universe didn't need a creator because it, in some twisted way, created itself? This isn't just philosophical noodling. Some cosmological models flirt with this very idea. Quantum fluctuations, the same unpredictable jitters that spawn particles from empty space, might have sparked the Big Bang. But here's the twist. Those fluctuations could rely on the very laws of physics that emerged from the Big Bang itself. It's like a flame that ignites the match that lit it, a loop where the effect predates the cause. Even the arrow of time, which we assume always points forward, might be an illusion. In certain interpretations of quantum mechanics, particles can influence each other backward in time, as if the future were whispering to the past. The implications are dizzying. If the universe bootstrapped itself into existence, it means there's no ultimate first cause. no uncaused cause that philosophers and theologians have debated for centuries. Existence becomes a Möbius strip of causality, where asking what started it all might be as meaningless as asking which came first, the chicken or an egg that was always there. Some theorists take this further, suggesting our universe could be one in an endless chain of cyclical cosmoses, each birthing the next in an infinite dance of creation and destruction. But the paradox also exposes a haunting gap in our knowledge. If the universe truly is self-originating, what does that say about the fine-tuning of its constants, the precise balance of gravity, the strength of nuclear forces? If these weren't set by some external hand, why do they seem so perfectly calibrated for life? One radical answer: we're here because the universe had to be this way to create observers who could ask the question. It's as if reality folds back on itself, not just in space and time, but in meaning. The Bootstrap Paradox doesn't just challenge our ideas of origin, it unravels the very notion of linear explanation. Maybe some truths are circular, their beginnings and endings smudged into irrelevance. And if that's the case, then the greatest cosmic joke might be this: the universe didn't come from anywhere, it just is, always was, and always will be, a riddle wrapped in an enigma spinning in the void. Imagine flipping a coin, but until you look at it, it's neither heads nor tails somehow, it's both at once. This is the bizarre reality of quantum particles, which exist in a haze of possibilities until the moment they're observed. Then, and only then, do they choose a single state. This is the observer effect, a phenomenon so counterintuitive that it forces us to ask, does reality even exist without someone or something to witness it? At the heart of this paradox lies a question that straddles the line between physics and metaphysics. What exactly counts as an observer? Take the famous double-slit experiment, where particles like electrons are fired at a barrier with two openings. When no one's watching, these particles behave like waves, creating an interference pattern on the other side, as if they've passed through both slits simultaneously. But the moment a detector is placed to observe which slit each particle goes through, the wave-like behavior vanishes. The particles suddenly act like discrete objects, as if they're aware of being watched. Here's where things get eerie. It doesn't matter if the observer is a human scientist or a machine, the mere presence of measurement changes the outcome. So is consciousness irrelevant, or is the universe playing by rules we don't yet grasp? Some interpretations of quantum mechanics, like the Copenhagen school, argue that observation causes the collapse of a particle's probability wave into a definite state. But they sidestep the thorny issue of what constitutes an observer. Does it require a mind, or is any interaction with the environment enough? The physicist John von Neumann took it further, suggesting that consciousness itself might be the trigger, an idea that veers into territory once reserved for philosophers. Meanwhile, the many worlds interpretation offers a wild alternative. Maybe the wave never collapses. Instead, every possible outcome plays out in a branching multiverse, and we're just trapped in one version of events. The implications ripple far beyond the lab. If reality is shaped by observation, could entire galaxies exist in uncertain states until some intelligence notices them? Are we, by virtue of being conscious, somehow responsible for solidifying the universe around us? Or is this all a misinterpretation, a confusion between measurement and consciousness? After all, a photon hitting a camera sensor isn't so different from one hitting a retina. The universe doesn't care whether the data ends up in a human brain or a hard drive. Yet the observer effect lingers as one of quantum theory's greatest unsolved puzzles. It challenges the very notion of an objective reality. suggesting that the universe might be less a fixed stage and more a participatory dance. Every time we probe deeper, we're reminded that the act of looking doesn't just reveal reality, it might just be creating it. And that's a paradox that doesn't just defy logic, it redefines what it means to exist. Every story has an ending, but what if the universe's final chapter isn't a dramatic collapse or a fiery implosion, just a slow, silent fade into darkness? That's the unsettling premise of the heat-death paradox, a cosmic dilemma that pits the laws of thermodynamics against our very understanding of time itself. Picture a cup of coffee left untouched on the counter. Steam rises, heat dissipates, and eventually it reaches room temperature, a state of equilibrium where no energy flows in or out. Now imagine that same principle applied to the entire cosmos. Stars burn out, black holes evaporate, and over trillions upon trillions of years, all energy spreads so thin that the universe becomes a vast, lukewarm void. No more light, no more motion, no more change. This is heat-death, the ultimate triumph of entropy. But here's the twist that keeps physicists awake at night. If heat-death marks the end of time, a state where nothing happens and nothing can ever happen again, how does the universe reach that point? How can time take forever if forever implies time still exists? It's like saying a movie ends when the credits freeze, but the projector keeps running anyway. This paradox forces us to confront the slippery nature of time, which isn't just a backdrop to events, but something woven into the fabric of reality itself. Some theorists propose that time, as we know it, might simply cease to have meaning in a heat-dead universe. Without change, without causality, the concept of before and after evaporates. In this view, heat-death isn't an event in time, it's the end of time's very existence. Others speculate that quantum fluctuations could spark new big bangs in the void, birthing fresh universes in an endless cycle. But even this raises questions. If time stops, how can anything wait for a fluctuation to occur? The paradox exposes how little we grasp the deep link between time, entropy, and the universe's fundamental structure. Perhaps the most haunting implication is this: if heat-death is inevitable, does anything we do truly matter in the long run? Philosophers have wrestled with this for centuries, but modern cosmology gives it new urgency. Yet there's a strange comfort in the paradox too. It reminds us that the universe is more than a clock winding down. It's a puzzle with layers we've barely begun to peel back. And until we solve it, the heat-death paradox stands as both a warning and an invitation to cherish the fleeting light of existence while daring to ask what lies beyond the end of time. Imagine stepping into a pitch-black room and declaring it freezing cold, only for someone else to walk in and insist it's warm. Now picture that room as empty space itself. According to the Unruh Effect, temperature isn't just something we measure. It's something we create by how we move through the universe. This bizarre phenomenon reveals that an astronaut accelerating through what appears to be a vacuum would actually feel the glow of heat, as if bathed in invisible radiation. Yet someone floating at a constant speed in that same empty void would detect nothing but icy darkness. How can two observers disagree so fundamentally about something as basic as temperature? The answer lies in the quantum froth of empty space. Contrary to popular belief, a vacuum isn't truly empty. It's a seething ocean of virtual particles that constantly blink in and out of existence. Normally, these particles cancel each other out so perfectly that we never notice them. But acceleration changes the game. When you're speeding up, your motion through this quantum soup disturbs those fleeting particles, dragging some of them into reality like a boat churning up waves. To the accelerating observer, these particles manifest as real heat, a phenomenon predicted by physicist William Unruh in 1976. The faster you accelerate, the hotter empty space appears, an effect that would make a rocket pilot feel like they're flying through a thermal bath, even in the deepest void between galaxies. What makes this so mind-bending is the implication that temperature isn't an objective property of the universe, but a subjective experience shaped by motion. A thermometer attached to a speeding spaceship wouldn't just malfunction, it would genuinely detect heat where none existed before. This challenges our everyday intuition that a cup of coffee stays hot whether we're sitting still or driving in a car. Einstein's relativity already taught us that time and space are flexible, but the Unruh effect suggests even something as tangible as warmth is up for debate. The paradox deepens when we consider black holes. Stephen Hawking showed that these cosmic monsters emit radiation due to quantum effects near their event horizons, a discovery deeply linked to the Unruh effect. An astronaut falling into a black hole would perceive the vacuum as cold and empty, while someone watching from afar would see the doomed traveler bathed in Hawking radiation's heat. Both perspectives are equally valid, forcing us to ask which temperature is real. The answer might be neither or both. Reality, it seems, wears different masks for different observers. Yet the most unsettling question remains: if motion can conjure heat from nothing, could the warmth we feel right now be an illusion? Earth orbits the Sun at 67,000 miles per hour, while our solar system careens through the galaxy at 500,000. Are these motions subtly heating the space around us in ways we've never noticed? The Unruh effect blurs the line between physics and perception, leaving us to wonder whether the universe has a true temperature, or if it's all just a matter of perspective. One thing's certain: the next time you shiver in the night, remember the cold might not be out there at all. It could just be you standing still in a quantum sea of infinite possibilities. Imagine tossing a coin in New York and watching another coin in Tokyo instantly land the same way. No delay, no signal, just perfect synchronization. This is the eerie reality of quantum entanglement, the phenomenon at the heart of the Einstein-Podolsky-Rosen Paradox. When two particles become entangled, they share a mysterious bond that defies distance. Measure one's spin or polarization, and its partner, no matter how far away, snaps into a corresponding state faster than light could ever travel between them. Einstein famously called this spooky action at a distance, not just because it violated his theory of relativity, but because it hinted at a universe where particles might be whispering secrets to each other behind the curtain of spacetime. The paradox cuts to the core of quantum mechanics' strangest claim: reality isn't local. In our everyday world, if something happens here, its effects take time to reach somewhere else, like waiting for ripples from a pebble tossed in a pond to reach the shore. But entangled particles don't play by those rules. Experiments have confirmed this again and again, with particles separated by hundreds of miles responding instantaneously to measurements of their partners. It's as if the universe has a hidden switchboard connecting everything in ways we can't see. So how does this happen? One possibility is that entangled particles aren't truly independent. They might carry hidden variables, predetermined instructions set at the moment of entanglement that dictate their behavior. But physicist John Bell proved in the 1960s that most hidden variable theories clash with quantum predictions, leaving us with a stark choice: either abandon the idea of an objective reality independent of observation, or accept that the universe is fundamentally non-local, with influences threading through space faster than light. The implications are staggering. If entanglement links particles across cosmic distances, does that mean the universe is a vast, interconnected web where separation is just an illusion? Some interpretations, like quantum pilot wave theory, suggest particles are guided by unseen waves that transcend space. Others, like the many worlds interpretation, propose that every measurement splits reality into branches, with entangled particles simply mirroring each other across parallel timelines. Yet the most unsettling question remains: what if entanglement isn't about particles communicating at all? Maybe the problem lies in our assumption that they are ever truly separate to begin with. In a holographic universe where reality is a projection of deeper, entangled information, distance might be a trick of perspective, like two shadows cast by the same object, moving in sync no matter how far apart they seem. The Einstein-Podolsky-Rosen Paradox doesn't just challenge physics, it rewires our intuition about existence itself. Every time we confirm entanglement in labs, we're glimpsing a layer of reality where the ordinary rules dissolve, where particles dance to a rhythm we can't yet hear. And until we crack this code, the universe's spookiest secret remains. Somehow, in ways we don't understand, everything is connected. If advanced civilizations exist, why aren't they building skyscrapers around stars? That's the puzzle at the heart of the Dyson sphere paradox. Imagine a structure so vast it encircles an entire sun, capturing every drop of its energy, a feat of engineering so grand it would reshape the cosmos. Physicist Freeman Dyson first proposed this idea in the 1960s, suggesting that any civilization reaching a certain technological peak would inevitably construct such megastructures to fuel its growth. Yet decades of scanning the skies have turned up no definitive signs of these cosmic power plants. Not a single star dimmed in the telltale pattern of an artificial shell, no infrared signatures of waste heat radiating from alien industry. The silence is deafening, and it forces us to ask, if they're possible, where are they? One possibility is that Dyson spheres are harder to build than we think. The energy required to dismantle planets, the precision needed to stabilize solar collecting arrays, these challenges might be insurmountable even for advanced civilizations. Or perhaps there's a darker explanation. Any species capable of harnessing a star's full power might also possess the means to self-destruct, vanishing before they can complete their cosmic engineering. This aligns with the Great Filter hypothesis, the idea that some catastrophic barrier, nuclear war, runaway AI, ecological collapse prevents civilizations from reaching interstellar scales. If that's true, the absence of Dyson spheres isn't just a curiosity, it's a warning written in the stars. But there's another, even stranger option. What if these megastructures are everywhere and we're just not seeing them correctly? A truly advanced civilization might not use clumsy solid shells but swarms of energy-capturing satellites, invisible to our telescopes. Or they could have moved beyond stars entirely, tapping into darker, more exotic energy sources we haven't discovered yet. Some theorists speculate that black holes, not stars, might be the ultimate power plants for civilizations millions of years ahead of us. If that's the case, we're like ants searching for campfires in a world lit by nuclear reactors. Then there's the unsettling thought that we're looking at this all wrong. Maybe Dyson spheres aren't rare because civilizations fail. Maybe they're rare because intelligence itself is a fluke. Life might spark easily across the universe, but perhaps the leap from single-celled organisms to star-faring engineers is so improbable that Earth is one of the only places it's ever happened. Or worse, what if we're the first in a universe 13.8 billion years young? It's possible that sentient life is only just awakening, and the age of megastructures hasn't even begun. The Dyson sphere paradox doesn't just challenge our search for aliens, it holds up a mirror to humanity's own future. If we survive the next few centuries, will we too build rings around the sun, our hunger for energy reshaping the solar system? Or will we join the silent majority of civilizations that never made it that far? The cosmos isn't just asking us where the aliens are. It's asking whether intelligence, in the end, is a candle flickering in the dark or a fire waiting to be lit. What if death isn't the end but an illusion, a trick played by the universe to convince you that your story is over? The quantum immortality paradox takes the many worlds interpretation of quantum mechanics and twists it into something deeply personal. Imagine you're playing Russian roulette with a gun that has 1,000,000 chambers and only one bullet. Statistically, you'd almost certainly survive, but in the many worlds view, every trigger pull splits reality. In most branches, you hear a harmless click, but in one, the gun fires. Here's the catch: you, the conscious observer, can only experience the timelines where you're alive. From your perspective, you'd keep surviving against impossible odds, watching as the universe seemingly bends to keep you breathing. This isn't just theoretical macabre. The paradox forces us to confront the nature of consciousness itself. If every quantum decision spawns alternate realities, then there's always a version of events where you narrowly escape death, whether it's dodging a fatal car crash by milliseconds or surviving a terminal illness through a fluke recovery. To the outside world, you'd appear impossibly lucky or worse, cursed. But to you, it's just life unfolding as usual, with no awareness of the timelines where your luck ran out. Critics argue this idea conflates probability with perception. Just because there's always a universe where you survive doesn't mean you're magically drawn to it. It just means your consciousness stops where the bullet lands. But proponents counter that the very act of observation might anchor you to the livable branches, like a cosmic version of the observer effect. After all, if consciousness arises from quantum processes in the brain, maybe it can't exist in states where those processes cease. The implications are as unsettling as they are profound. Would aging just be a slow-motion version of this paradox, with your consciousness hopping timelines until every possible path leads to death? Could this explain near-death experiences, where people report vivid visions as their brains scramble through quantum possibilities? And what does it mean for identity? Are you even a continuous entity, or just a thread stitched together by survival? Perhaps the most haunting question isn't about physics, but psychology. If quantum immortality is real, how would anyone ever know? The universe would look exactly the same to you right up until the moment it doesn't. And by then, there'd be no one left to ponder the paradox. The theory remains untestable, a ghost in the machinery of reality, whispering that death might not be the end, but a door we simply never walk through. Empty space isn't supposed to weigh anything, that's why we call it empty. But quantum physics paints a far stranger picture. According to the rules governing the subatomic world, the vacuum of space should be a seething, bubbling cauldron of energy, packed with virtual particles flickering in and out of existence. These fleeting fluctuations aren't just theoretical, they've been measured in labs, and their energy density should be staggering. In fact, when you crunch the numbers, the vacuum's energy ought to be so intense that it would warp spacetime with enough force to tear the universe apart. And yet, when we look out into the cosmos, space appears almost perfectly calm. This jaw-dropping mismatch, 120 orders of magnitude between prediction and reality, is the vacuum catastrophe, one of the most embarrassing unsolved problems in physics. How could the numbers be so spectacularly wrong? One possibility is that we're missing something fundamental about how quantum fields interact. Maybe opposing forces cancel each other out with near-perfect precision, like two colossal waves crashing together and leaving behind only the faintest ripple. String theorists have proposed that hidden dimensions or undiscovered symmetries could be balancing the scales, effectively erasing the vacuum's energy before it can affect the cosmos. But even if such a cancellation mechanism exists, why would it balance out to something so close to zero rather than just a slightly smaller, but still enormous number? It's like tossing a coin and having it land on its edge not just once, but every single time across the entire universe. Then there's the unsettling alternative. What if our theories are fundamentally flawed? Quantum field theory and general relativity, the twin pillars of modern physics, have been tested to incredible precision in their respective domains. But when they come together to describe the vacuum, they produce nonsense. This isn't just a minor glitch, it's a screaming red flag that we're missing a deeper layer of reality. Some researchers speculate that dark energy, the mysterious force accelerating the universe's expansion, might be a faint remnant of this cancelled-out vacuum energy. If true, it would mean that empty space isn't quite empty after all, just far, far weaker than it has any right to be. The vacuum catastrophe isn't just a numbers game, it's a crisis of intuition. We're forced to confront the possibility that our most successful theories might be approximations, shadows cast by a reality we don't yet understand. Every time we peer into the void, we're reminded that the universe's greatest mysteries aren't always written in the stars. Sometimes they're hidden in the silence between them. Imagine stepping toward a black hole, bracing for the tidal forces that will stretch you like taffy, only to realize the true danger isn't the crushing gravity, but an invisible wall of fire lurking at the event horizon. This is the Firewall Paradox, a cosmic nightmare where two of physics' most successful theories, quantum mechanics and general relativity, predict wildly different fates for anyone daring to cross a black hole's threshold. According to Einstein, falling past the event horizon should feel uneventful at first, a smooth descent into oblivion where gravity's pull grows steadily stronger. But quantum mechanics paints a far more violent picture, a searing barrier of high-energy particles that would vaporize you instantly, turning your grand adventure into a split-second barbecue. How can the same universe allow such contradictory realities? The paradox traces back to Hawking radiation, the slow leak of energy that causes black holes to evaporate over eons. Quantum theory suggests that particles escaping the black hole must be entangled with particles falling inward, a delicate quantum handshake that preserves information. But here's the catch. If the outgoing radiation keeps its entanglement with the black hole's interior, it can't also be entangled with earlier radiation, a violation of quantum rules that demand particles can't be double entangled. To resolve this, physicists proposed the firewall, a brutal solution where the entanglement snaps at the horizon, releasing enough energy to incinerate anything passing through. It's like a cosmic copyright enforcement, shredding forbidden quantum connections in a blaze of lethal radiation. Yet this creates an absurdity. Relativity insists the event horizon should be unremarkable, a point of no return but not a physical barrier. An astronaut crossing it wouldn't notice anything amiss until gravity's gradient pulls them apart. But if firewalls exist, then the horizon isn't just a boundary, it's a death trap, fundamentally altering the nature of black holes. Worse, it implies that the laws of physics aren't just incomplete, they're catastrophically wrong in extreme environments. Some theorists argue firewalls might be artifacts of our flawed math, like seeing a mirage in the equations. Others suggest the paradox reveals a deeper truth. Space-time itself might be emergent, stitched together by quantum entanglement. If so, the firewall could be a seam where the fabric frays, exposing the stitches beneath. There's even a radical idea that black holes don't have interiors at all. What we perceive as a singularity might just be a scrambled hologram on the horizon's surface, with the firewall acting as a shredder for anything trying to enter. The stakes couldn't be higher. If firewalls are real, they'd rewrite our understanding of gravity, quantum mechanics, and the nature of reality itself. If they're not, we're left with an equally profound puzzle. How does information escape a black hole without breaking the universe's rules? The Firewall Paradox isn't just about the fate of doomed astronauts, it's a battle for the soul of physics, a clue that the answers we seek might lie in the flames. Magnets are everywhere, stuck to your fridge, humming inside your headphones, even guiding migrating birds across continents. But there's a catch. Every magnet you've ever encountered has two poles, a north and a south. Snap one in half, and you don't get isolated poles, you just create two smaller dipoles. This seems like a quirk of nature until you realize it's a cosmic anomaly. Because according to some of our most elegant physics theories, single magnetic poles called monopoles should be as common as electrons. They're predicted to have formed in the seething chaos of the early universe, frozen into existence as space-time expanded and cooled. And yet, despite decades of searching, not a single definitive monopole has ever been detected. Their absence isn't just a curiosity, it's a gaping hole in our understanding of how the universe works. The case for monopoles starts with symmetry, a guiding principle in physics. Just as positive and negative electric charges exist independently, grand unified theories, which attempt to merge electromagnetism with the strong and weak nuclear forces, demand that magnetic monopoles should exist too. In the unimaginable heat of the universe's first moments, these theories suggest the forces of nature were indistinguishable, fused into a single superforce. As the cosmos expanded and cooled, that symmetry broke, crystallizing into the distinct forces we know today. And just as cracks form in ice as it freezes, these phase transitions should have created topological defects, knots in spacetime where magnetic charge couldn't smooth itself out. These knots would be monopoles, relics of a more symmetrical era, buzzing through the cosmos like cosmic stragglers from the dawn of time. So where are they? The simplest answer is that we've been looking in the wrong places. Monopoles, if they exist, would be staggeringly massive, perhaps as heavy as a bacterium, but squeezed into a space smaller than a proton. Their sheer density means they'd punch through matter like bullets through tissue, leaving faint trails of ionization in their wake. Experiments have scoured everything from lunar rocks to ancient mica crystals, searching for these telltale tracks. Others have rigged superconductors to catch passing monopoles, their quantum properties making them ultra-sensitive to magnetic anomalies. Even cosmic rays have been scrutinized for hints of these elusive particles. But so far, nothing, not a whisper, not a trace. The silence is deafening, and it forces physicists to confront uncomfortable possibilities. Maybe grand unified theories are wrong, and the universe never had the symmetry required to spawn monopoles. Or perhaps inflation. The brief period of exponential expansion after the Big Bang stretched spacetime so thin that monopoles were diluted to near zero density, leaving just one or two lurking in the entire observable universe. There's even a radical idea that monopoles aren't particles at all, but hidden dimensions folded into themselves, their magnetic charge leaking into our reality as faint, undetectable echoes. But the most tantalizing clue might come from an unexpected place: quantum materials. In recent years, physicists have engineered synthetic monopoles in exotic states of matter, where collective behaviors of electrons mimic the properties of these hypothetical particles. These aren't true monopoles, they're emergent phenomena, like whirlpools in a river that behave as independent objects. Yet their existence hints that nature might know how to build monopoles after all, just not in the way we expected. The Monopole Paradox isn't just about missing particles. It's a test of whether our most ambitious theories of the universe align with reality. every null result, every empty detector, chips away at the elegant equations that say monopoles should exist. And until we find them or prove they were never there to begin with, we're left with a puzzle that defies not just logic, but the very symmetry we thought governed the cosmos. The universe, it seems, has a way of keeping its secrets even when we're certain we've cracked the code. Look up at the night sky in any direction, and you'll find the same story: regions of space separated by billions of light years, regions that have never exchanged so much as a photon, are eerily identical in temperature. It's as if every corner of the universe received the same memo at the exact same moment, down to a fraction of a degree. This is the horizon problem, one of cosmology's most baffling puzzles. If the speed of light is the ultimate speed limit, how did patches of space too far apart to ever interact manage to sync up so perfectly? The problem starts with the cosmic microwave background, the afterglow of the Big Bang. This faint radiation blanket paints the sky with near-perfect uniformity, varying by less than 1 part in 100,000. But here's the catch: for two regions to reach thermal equilibrium, they need time to exchange energy, like 2 cups of coffee evening out to room temperature when placed side by side. Yet in the early universe, regions now on opposite sides of the observable cosmos were too far apart for light or heat to have shuttled between them, even in the universe's 13.8 billion year lifetime. By all rights, they should be as different as fire and ice. Instead, they match like twins separated at birth. Physicists proposed cosmic inflation as a solution, a mind-boggling idea that the universe underwent a fleeting, exponential expansion in its first fraction of a second. This hyper-stretching would have taken a tiny, homogeneous patch of space and blown it up to scales far larger than our observable universe, smoothing out any irregularities before the cosmos settled into its current, more leisurely expansion. Inflation solves the horizon problem by ensuring everything we see today came from a region small enough to have once been in causal contact, but this raises its own mysteries. What triggered inflation? Why did it stop? And most unsettlingly, if inflation can stretch space faster than light, does that mean the true universe is unimaginably larger than what we can observe, with our entire cosmic horizon just a speck in a vastly inflated landscape? The paradox deepens when we consider alternatives. Could there have been some pre-Big Bang connection that allowed distant regions to talk to each other? Some theories, like conformal cyclic cosmology, suggest our universe is one in an endless chain, with each cycle's end seeding the next Big Bang, potentially preserving information across epochs. Others propose that the speed of light wasn't always constant, allowing heat to propagate faster in the early universe. But these ideas come with their own baggage, from untestable predictions to conflicts with well-established physics. Perhaps the most radical interpretation is that the uniformity isn't a coincidence but a clue, a sign that the universe's structure is fundamentally different from what we perceive. Holographic principal theories suggest that what we see as three-dimensional space might be a projection of information encoded on a distant, two-dimensional surface, where locality and distance are illusions. In this view, the horizon problem vanishes because separation itself is a mirage. Every part of the universe was always connected at a deeper level, like pixels on a screen sharing the same underlying code. The horizon problem doesn't just challenge our models of the early universe. It forces us to confront how little we grasp about the nature of reality itself. Is the cosmos uniformity a relic of inflation, a shadow of a deeper physics, or something else entirely? Until we find answers, the night sky remains a silent witness to a coordination act so perfect, it defies every rule we thought we knew. From the silence of alien civilizations to the illusion of time, these 20 paradoxes peel back the curtain on a universe that refuses to play by our rules. Each one isn't just a puzzle, it's a crack in the foundation of our understanding, revealing glimpses of a reality far stranger than anything we could invent. Think about it, we've mapped the human genome, split the atom, and sent probes beyond our solar system, yet the cosmos still tosses us riddles that leave even the sharpest minds humbled. That's the beauty of these enigmas, they're not dead ends, but invitations. Every time we hit a wall, it's a sign we're asking the wrong questions, or maybe not dreaming boldly enough. Consider how the Fermi Paradox forces us to grapple with our own significance. Are we alone, or is the universe hiding its inhabitants in ways we can't yet fathom? The quantum Zeno effect blurs the line between observer and reality, suggesting that consciousness might be more than a passive spectator, and the Bootstrap Paradox. It turns the idea of cause and effect into a cosmic joke where the universe could be its own creator. These aren't just thought experiments, they're clues scattered across physics, philosophy, and cosmology, waiting to be pieced together. What's thrilling is that we're living through the golden age of discovery. Telescopes like James Webb are rewriting the story of the early universe, while quantum computers tease us with the possibility of simulating realities we've only dreamed of. Every paradox we've explored today is a frontier, a challenge to the next generation of thinkers. Maybe you'll be the one to crack the mystery of dark matter or find the flaw in the simulation hypothesis. Or perhaps you'll stumble upon a paradox so baffling it redefines science itself. So, which of these cosmic conundrums lingers in your mind? Is it the haunting emptiness of the great silence, or the way entangled particles defy space and time? Whatever it is, hold on to that curiosity. It's the same spark that's driven every leap in human knowledge. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's the most exhilarating part. The journey doesn't end here. Hit like, subscribe, and join us as we keep peeling back the layers of reality, one paradox at a time. The cosmos has plenty more secrets to share. Are you ready to uncover